Hi there, I'm Alex and I'm going to talk to you about magnetism. What is it, how does it work, and how do we use it? So first of all, what is it? Magnetism is basically a force that makes objects either attract, come together, or repel, push apart. Magnetism is caused by the flow of electricity. This can be shown by attaching a copper wire to a battery. The electricity will flow through the wire and make it become an electromagnet, and then it will attract paper clips or other objects. So what's a magnetic field? A magnetic field is just basically the area around the magnet where its magnetic force applies. It flows from north to south, outside of the magnet, and south to north, inside of the magnet. These are magnetic lines of force. They just show where the magnetic field is. They don't actually flow, but they all are described as flowing and are drawn with arrows.
So we see that magnets have north and south poles. Poles are just the part of the magnet with the strongest attractive or repulsive forces. Different poles, north and south, attract, while like poles repel.
There are two different sources of magnetism. There's electromagnetism, which is using electricity like with the copper coil, or there are spin magnetic moments, which we need a little bit of quantum mechanics to understand.
So we know that atoms make up everything, and they're a very small unit of matter. They're made of positive protons and neutral neutrons in the nucleus, with electrons orbiting outside. Well, actually, the electrons more exist in a sort of cloud around the nucleus. They exist in orbitals. An orbital is just an area where the electron has about a 90% chance of being. Each orbital can hold 2 electrons. This is the periodic table, but it's colored according to the orbitals. The s orbitals are purple, the d orbitals are orange, the blue ones are the p orbitals, and the f orbitals are green. Now, electrons fall in a certain order. Start with hydrogen at the top. Hydrogen has 1 electron, which exists in the 1s orbital. Helium has 2 electrons, but each orbital holds 2 electrons, so its electron also exists in the 1s orbital. Then we go down to the 2s orbital. As we move over, we get to the p orbitals. There are only 2 electrons in each orbital, but there are 3 separate p orbitals. There are 5 d orbitals and 7 f orbitals. So we start with the 1s orbital, which is just a sphere, which would contain 2 electrons, and then we go to the 2s orbital, which is the same as the 1s orbital, except it's just bigger. When we move to the p orbitals, there's a pxy, a pxz, and a pyz, which would be 3D. The only difference is just the way they're orientated. They all look like dumbbells. As you would move on, you'd have the 3s orbital and 3p, and they just keep getting bigger. The f orbitals and the d orbitals are in different shapes. This diagram, called an off-bow diagram, shows the electron configuration of an atom. You'd start with hydrogen in the 1s with 1 electron, then helium with 2, then you move up to the 2s, then to the 2p, and so on. Each electron has either a clockwise spin or counterclockwise spin. Clockwise is an up arrow, while counterclockwise is a down arrow. Also sometimes as positive half or negative half. The electrons in an orbital have to have opposite spins. But when you get to a 2p orbital, which has more than one type of p orbital, you have to half fill every orbital before an orbital gets 2 electrons. This means that some electrons can get left unpaired, which is important in the concept of magnetism.
So we know that magnetism is caused by the flow of electricity, and it has to be flown. It cannot be stationary. But what determines that this is a magnet over this? Neither of these things are hooked up to electricity to make them the electromagnet. So we look at our second source of magnetism, spin magnetic moments. This is just when an object's electrons line up with an existing magnetic field. To understand this a little better, we need to look at the different types of magnetism. The first being diamagnetism. Diamagnetism is shown by, well, everything, even things we would consider not a magnet. That marker was not a magnet, but it does show diamagnetism. Diamagnetism is shown by everything, but can be overtaken by the other forms of magnetism discussed later. Diamagnetic objects are usually the objects that have paired electrons and no unpaired electrons. The paired electrons are perfectly happy, so when they come in contact with the magnetic field, they orient themselves to oppose it, which actually makes a very small repulsion, but not big enough to be seen with their eyes.
Watch the diamagnetism.
Paramagnetic objects actually do have a few lone pairs, and they can orient themselves with the magnetic field to create a small magnetic force. But they can also orient themselves not with the magnetic field at all. So paramagnetism can also only be picked up with super-sensitive equipment. Now, ferromagnets, what we would normally consider to be magnets, like this horseshoe magnet. They have lone paired electrons, and when they come in contact with the magnetic field, they line up to create a magnetic force. Now, the electrons in a ferromagnetic substance are not always lined up. They can be all over the place. But once they come in contact with this magnetic field, they line up. They can even keep this magnetic force after the magnetic field has left.
There are 2 other types of magnetism as well. There is antiferromagnetism, where the order is opposite of whatever its neighbor is. And there's also ferrimagnetism, where they're equal for or against the magnetic field. But the ones that are against have a much lesser magnitude than the ones that are aligned with the magnetic field. So to sum it up, in ferromagnetism, there are unpaired electrons, and they work together well. In paramagnetism, there are unpaired electrons, but they might not be all on the same page. And in diamagnetism, the paired electrons want nothing to do with this magnetic field tug-of-war.
So, there's another form of magnetism that we can talk about, which is called super diamagnetism. And as the name implied, the material should be super diamagnetic. Diamagnetic materials show repulsion, so super diamagnetic materials show a much stronger repulsion. These materials are usually known as superconductors. Superconductors are a little bit different from diamagnetic materials. The definition of a superconductor is a material that conducts electricity with no resistance. Resistance is just the force that works against the flow of electricity. So if you have a wire made out of a superconducting material, you can flow electricity through it without any of the electricity being wasted due to resistance. All magnets have what is called a Curie temperature. That means when a magnet is heated up to this temperature, it loses its magnetic properties. When the magnet is heated up to this temperature, its atoms gain a lot more energy, so they move around a lot more. That makes it hard for the unpaired electrons to line up with the magnetic field, meaning the magnet has no magnetic properties at that point. Superconductors have what is called a critical temperature, sort of the opposite. When a superconductor is cooled down to this temperature, that's when its superconducting properties start. Above this temperature, it has no superconducting properties at all. When a superconductor is cooled past the critical temperature and subjected to a magnetic field, something strange happens. The superconductor actually repels the magnetic field. This is because the superconductor does not allow the magnetic field to cross through it, except for a few nanometers deep on the surface. This is because the superconductor sets up tiny electric currents on the surface called persistent currents, which repel the magnetic field. This is called the Meissner effect.
So, have you ever seen those superconductors that almost seem to levitate? Well, there are two different types of superconductors, type 1 and type 2. The difference is that type 1 have one critical field, while type 2 have two. Type 1 superconductors are either a superconductor or not a superconductor, depending on the temperature and magnetic field they're subjected to. Type 2 superconductors can be a superconductor, not a superconductor, or be sort of both. That means they can be both attracted to a magnet and repelled, which causes a sort of levitation that we see. When you see a superconductor almost floating above a magnet, this is called flux pinning and only happens in type 2 superconductors. This is because they have that second critical field, that area where it's both a superconductor and not a superconductor. This is because of apocosa vortices. Since it's sort of not a superconductor, it will let the magnetic field go into this superconductor in the form of vortices, which allow it to attract and repel the magnet at the same time, leaving it pinned in midair.
So why should we care? Other than being super awesome, superconductors have tons of uses. From MRI machines to look inside our bodies, to NMR machines, to particle accelerators, to even maglev trains. The only problem is superconductors have to be cooled to such low temperatures to show their superconducting properties. But with high temperature superconductors, we may have even a whole new group of uses for them. That's not all. Magnetism is used a ton in our lives. From compasses, to cranes, to speakers, to even our fridges. No one can deny magnetism is awesome. Thank you.